right, so as I promised, here is a video telling you a little bit about black holes. And along the way, we're going to talk a little bit about general relativity because some of those concepts are relevant to black holes. So hopefully you enjoy learning a little bit more about them and basically learn how nuts this whole idea is of a black hole. So the first thing I wanted to do is just kind of remind you of what we've looked at so far. So we talked about the end stages of stars, stars like the sun, massive stars, and then what we're doing today is really massive stars where their remnant is big enough that we form a black hole. So for a star like the sun or a little bit bigger, as long as the core that remains after it becomes a planetary nebula is less than 1.4 times the mass of the sun, that remnant will become a white dwarf. Remember that 1.4 times the mass of the sun was called the Chandrasekhar mass. It was, from an Indian physicist who postulated that if the mass was larger than that, it would not be able to hold itself up under the force of gravity and would continue to collapse. Then if we have a remnant that is somewhere between that Chandrasekhar mass, 1.4 times the mass of the sun, but less than 2.8 times the mass of the sun, we would end up with a neutron star. And that's what we looked at in class most recently. Remember, a neutron star and a pulsar are basically the same thing, although it's sort of a case of semantics. When we observe a pulsar, we are looking at a neutron star because we are seeing the signals coming from it as it rotates very quickly. It's actually entirely possible for a neutron star to be in the sky, but because that beam of radiation never intersects the path of the Earth, we actually don't ever observe it. Finally, what we're going to look at today is the remnant of a star that's bigger than 2.8 times the mass of the sun. That is going to collapse into what we call a black hole. In order to have a better understanding of what a black hole is, we want to talk about this term called escape velocity. I think that you probably read about it, but I don't think we actually talked a lot about it, if at all, in class. So let's just think about just throwing a ball here on Earth. If you throw a ball up in the air, eventually it's going to come back down. What's actually happening is the acceleration of gravity is slowing the ball down as it's moving upwards. When it gets to its highest point in its path, its velocity will be 0, and then it starts coming back down. Technically, we say that those velocities at that point as it's coming down are negative. So imagine you throw a ball up with a certain speed. You watch it go up to its highest point and come back down. You probably understand that if you throw it faster, it'll actually get higher in the sky. And so this is somewhat related to the idea of escape velocity, because if you think about the case where, what if I threw it so hard that when it got to its highest point where its velocity became 0, it was outside of the influence of Earth's gravity, so the Earth couldn't pull it back down. This is what we call escape velocity. In this picture, they're trying to illustrate that an object might be thrown first relatively slow, and you notice that that object actually does come down and it hits the Earth. If it's thrown faster, it still comes down, but it takes a lot longer. It gets much further, gets over here. If you throw it at exactly the right rate, it'll end up being in an orbit around the Earth. So it won't actually fall down, but it'll just kind of stay in a circular orbit around the Earth. And then finally, if we throw it a little bit faster, as we see right here, we can say that that's when we believe that it has reached escape velocity. So basically, every object in space has its own escape velocity. The escape velocity is actually reflective of how strong that object's gravitational field is. So let's just look at a couple different escape velocities just to get a sense of this. I wrote the expression for escape velocity. We don't have to do a calculation, but if you wanted to, you could. Big G is that gravitational constant. That was 6.67 times 10 to the minus 11. And then mass would be the mass of the object. So if we're talking about the Earth's escape velocity, it would be the mass of the Earth. If we were talking about Jupiter, it would be the mass of Jupiter. And then finally, the big R is the radius of the object. So the radius of the Earth or the radius of Jupiter, whatever we're talking about. So on the left-hand side of this slide, you see a couple different escape velocities. So the escape velocity from Earth is 11.2 kilometers per second. That's how fast you'd have to throw a ball to escape the Earth's gravity. Obviously, nobody can throw that fast, but you could send a spacecraft with that speed. Then you look at Jupiter's escape velocity and you see how much stronger it is. It's 60 kilometers per second, which, if you think about it, makes total sense because Jupiter is much larger than the Earth is. Mars is smaller than the Earth, and you notice that its escape velocity is about 5 kilometers per second. Then we go back to another large object, the Sun, the most powerful gravitational source in our solar system. The escape velocity from the Sun is 600 kilometers per second. And finally, I made a mistake here. So the neutron star is actually 150,000 kilometers per second. That was kind of purposeful to list the neutron star because that's about 1/2 the speed of light. And so that was just sort of a good one to list because as we talked about last time, the neutron star becomes extremely dense. Its gravitational field becomes extremely strong. And that really high escape velocity is reflective of its really strong gravitational field. So basically, the reason that I wanted to talk about the escape velocity is because this is how we define the sort of becoming of a black hole. If the escape velocity of the object, that is the black hole, exceeds the speed of light, then we've created a black hole. So how does that happen? So we go back to a star which would have exploded in a supernova, and you're left with a core that was made up of neutrons. That's, again, we're looking at the massive star. We had learned about neutron stars, which were those remnants that were left over after a massive star went supernova. And if you remember in the reading, that neutron star was held up by what we called the neutron degeneracy pressure. Sometimes I think of it as, think of the neutrons that are making up the core as marbles. And if you tried to squeeze a handful of marbles, you can only squeeze them so far. They're very effective at resisting any change in their volume because they're hard and they hit against each other and you just can't get them any smaller. And so that's how we can think of the pressure that's holding up the neutron star. But just like could happen for a white dwarf that was too massive, or a remnant from a smaller star that was too massive to be live as a white dwarf, you could have a remnant of a massive star that was basically too much stuff was left in that core of neutrons for the pressure of the neutrons to hold up against the force of gravity, which is trying to collapse it. So remember the battle between gravity and pressure. Those are the two forces that are really important in our stars that battle against each other. And so basically, when you have the remnant that's too large to allow gravity, allow the pressure to offset the gravitational force it's trying to collapse it, it just starts to collapse. And what's happening is, at this point, there is nothing to stop that collapse. That remnant will continue to get smaller and smaller against the force of gravity. And as it does, it becomes much more dense. Its gravitational field becomes extremely strong. And at some moment in time, the escape velocity of that remnant is equal to the speed of light and then quickly exceeds it. This is going to happen extremely fast. And one of the hallmarks of relativity and our physics is that nothing can travel faster than the speed of light. And if the gravitational field of this remnant is so strong that it cannot, you would have to travel faster than the speed of light to escape it, then essentially nothing can escape this gravitational field. It has become a black hole. Nothing can escape. We can never see what's happening on the inside of that black hole because of it, because there's no way for signals from within the black hole to come out past its borders and tell us what's going on. There's a special size of when the black hole kind of becomes a black hole, and we set it to the way that we find it is how big will the mass that is making up the black hole, how big will it be when its escape velocity is equal to the speed of light? And that's called the Schwarzschild radius. And sort of like if you have a region in space, and so it becomes sort of this radius, and so like inside here, black hole. And then this becomes what we call the event horizon. The idea is that I kind of like that name because I think it makes sense, because you can't find out what's going on within that event horizon. It's sort of like the borderline between the black hole and regular space. And so this is sort of how we think of the black hole. It's not really well understood. I'm going to post a video also that you might want to watch a couple, like 20 minutes of, and you will see, scientists who do this for a living struggling to sort of explain like what exactly is a black hole, because mathematically and in terms of physics laws, what we have within that event horizon is not really well explained, because you have an object that had a mass, say it was 3 times the mass of the sun, which collapsed into literally a point of 0 diameter. It has an infinite density. Doesn't really make any sense. But that's what we're talking about with black holes. Now, one of the things that I think people think about is that if you got close to a black hole, you just would be sucked into it. And that's not actually true. If you're a reasonable distance outside the event horizon, you will feel a strong gravitational field, but you won't feel like it's not like a cosmic vacuum cleaner. We could have a black hole where the sun is and the earth would not be sucked into it. And that's one of those misconceptions. So in order to kind of move a little bit forward, we're going to talk about this theory of general relativity, because it is related to the phenomena that we observe with black holes. And it was developed by Albert Einstein, that crazy physicist who lived and worked in the early 1900s. So we're going to talk a little bit about the principle of equivalence, which is that Einstein realized that if you were accelerating, like in a closed spaceship, you wouldn't really be able to tell whether what you observed was due to the acceleration of the spaceship or gravity. So he basically said that accelerating and gravity are the same. You can't tell the difference. They also found that in general relativity that the passage of time was slowed down by strong gravitational fields, and that gravity can be explained by saying that mass warps space and time. A lot of crazy stuff. So let's think about the principle of equivalence. So Einstein supposedly, there's a quote, I can't quote it directly, but when he was working in a patent office, I think in Switzerland, he realized that if he fell off his stool, that he wouldn't be able to feel his weight. And this kind of like was this breakthrough moment for him where he realized that acceleration and gravity could be thought of as equivalent things. So if that sounds kind of crazy to you, think about that every day as you walk around, sit around, lay around, you are always getting input from your surrounding environment that you are under the influence of gravity. So if I'm sitting in a chair like I am right now, I feel the force of the chair supporting me underneath me. If I stand, I feel the floor pushing back on my feet. I feel that. If I'm laying down, I feel, say, the support of the couch on me. And so you get this input constantly that you have weight. But if you would somehow, from a series of unfortunate events, end up in free fall, say let's make it harmless, you jump off a diving board. As you're jumping off, in a sense, you can't really feel your weight. And so here's just some sort of relevant ideas that you might or may not be familiar with, in how acceleration can actually affect how heavy you feel. If you are we use the elevator a lot, is kind of handy. And think about if you've ever gone to maybe like a nice hotel that's really has a lot of stories, or a building, a skyscraper that's very, very tall. A lot of times in those situations, the elevators will move pretty quickly because they got a lot of distance to cover. And so you can actually feel some funny sensations as that elevator's either moving up or down, because of the fact that the elevator is accelerating. If you have an elevator that's not that fast and just kind of moves at a constant speed, like we have right here in the left-hand side, so we don't have no acceleration, we have no acceleration. If you carried a scale with you into that elevator and it was just moving at a constant rate, your weight would be exactly as you would weigh yourself in your own bedroom. Now the next ones, if you're accelerating down, now think about those examples of those elevators in a really tall building. Sometimes, again, they move really fast. And if you go down, sometimes you almost feel like the elevator drops out from under you a little bit. And that's basically what's happening. If you were able to weigh yourself in a case where that's happening, you would see a lighter weight than normal because that accelerating elevator is affecting your weight. And likewise, if we go up in that elevator, it's almost like the floor of the elevator is accelerating into your feet and you feel a little bit heavier. And again, it's affecting how you feel. And then finally, this is not going to happen, but if the elevator somehow lost its connection to whatever's pulling you up or down and started just falling, you would never not be pressed against the floor anymore, and you would feel no weight. So this would be free fall. If the elevator analogy doesn't work for you, you might have experienced this somewhat on like some amusement park rides. So the reason that we talk about that is that in those cases, when you were in an accelerating, what we call a reference frame, that would be the elevator, it affected how you felt your weight. So the thought experiment, and for relativity, we have lots of thought experiments, is that if you're in a spaceship and you can't see outside, so it has no windows, and you are floating, how would you know if the spaceship was in free fall or if you were just outside the influence of any planet's gravitational pull? There's really no way for you to tell the difference. This is really sort of part of this idea of the principle of equivalence. Or if you're in a spaceship and your feet are on the floor, how do you know if the spaceship is accelerating upwards or you're just under the influence of gravity? So in this case here, on the left, this is a spaceship that is accelerating up, while this one is just stationary. And the little pictures inside of here are trying to reflect that the observations that people are making within the spaceship, again, remember, they can't see outside, are exactly that they would expect if they were under the influence of gravity. Someone is calmly sitting in a chair at a desk looking through her microscope. She doesn't feel like she's floating around. She's able to stay sitting. Someone is dropping a ball and it's falling to the floor of the spaceship, and someone else is watching that happen. Again, this is what we would expect. If we just stood up in our room and dropped a ball, it's going to fall. But in this case, from the outside, we can tell that this is all happening because the spaceship is accelerating upward. It's, in a way, creating the effect of the gravity through the acceleration. And in the right-hand side, everyone is sort of experiencing the same thing as the spaceship that was accelerating, but the reason that they are is because they are safely on the surface of a planet or the moon or something, and they're actually experiencing gravity. So the idea of the principle of equivalence is that these two cases you can see are exactly right, or exactly the same, but there's no way for anyone to perform an experiment to determine whether or not they're accelerating or they're under the influence of gravity. You just can't tell. That is what the principle of equivalence is. And so we're going to look at something kind of weird that can happen in our accelerating frame. So we're going to pretend that we're in a rocket, and because the rocket is accelerating, we're going to see light bend. So the important thing is that this is something that a person within the rocket would experience or would notice. Because as you see in this picture, if I look at this and observe what's happening from the outside, I don't see it. And this is another kind of crazy thing that we see in Einstein's theories of relativity, is that it always really matters where the observer is. So again, this is what we're going to do. We're going to say we're in a rocket and it's accelerating upwards. Here it is. And we want to concentrate on this picture right here. Let's say that we were on one side of the rocket, obviously because this light travels really fast. We want to make our rocket kind of big or be able to make really precise measurements. But if you put a pulse of light and you're over here and maybe you just turn on a laser really quickly and then turn it off, you know that laser is going to want to travel across the width of the rocket. But what's happening is in the time that the light is traveling, the rocket is also moving up. So what happens instead, if we're watching this light from inside the rocket, instead of just looking like it just goes straight across the rocket, by the time it gets over here, the rocket has moved up and it's going to be hitting lower on this wall than it would have if the rocket was not accelerating. And so what we see is that the light path has bent. It's crazy. The light's traveling in a crooked line, and it's all because of the acceleration. And so, because we've accepted this principle of equivalence, I don't know if you've accepted it, but we want you to. If this can happen in an accelerating frame of reference, it can also happen under the influence of a gravitational field. Einstein said that strong gravitational fields will bend light. And it's even better. He actually said that gravity, well, it wasn't really gravity. Well, he says gravity was the result of the warping and the bending of space and time. And this is why the light doesn't follow a straight path. So let's talk a little bit about this. So you might remember at some point, we probably talked about the force of gravity was the force between two objects. And we had this equation that you could calculate the force of gravity. And one of the characteristics of this expression is that when you're talking about the force of gravity between two objects, they're exerting forces on each other, but they're not touching each other. Usually when you talk about a force, it's through some sort of contact, like I'll push on you or I pull on a rope that's attached to something. But gravitational force is kind of different because we call it force at a distance. It's somehow one mass reaches across space and is able to attract another mass, and they kind of do it vice versa. They do it to each other. And that's kind of crazy. Like, we find that gravity obeys this law, but why? Why does it act like this? And so Einstein had this really interesting explanation. He said that this was because that space and time was actually warped by masses in space, and then it actually ended up affecting how objects travel. So we usually kind of think of it as sort of a two-dimensional surface, even though it's more than 2 dimensions. Like, think about the surface of a waterbed or a surface of a rubber mat. And if I place a heavy ball in it, like for instance here, this is actually supposed to represent the sun. Something that has a lot of mass, if we place it on that surface, the mass is going to pull it down. And so this is what we call about warping. And then what happens is if I have a star that over here and its light is traveling towards me along this line, when it hits this warping, it kind of bends around. Think about if you rolled another small ball, if you placed, say, a bowling ball on a waterbed, and then you rolled a ping pong ball towards it so that it didn't hit it, but it kind of got near it where that indentation was happening, the ping pong ball is going to sort of veer off as it hits that indentation. That's really how Einstein is explaining how gravity works. So here's some different pictures of this warping of space and time. Again, here you can kind of see in this picture, depending on the speed, there's different ways that an object can move around another planet. So here you can kind of see that in this situation, this object, right, whatever this is, might end up getting caught into an orbit around this planet where other objects, if they travel fast enough by, will just kind of bend, but they'll continue on their way. And in this picture here, you see that these different balls are having different effects on their space and time around them because they're just like different sizes, different masses. Like the yellow one must be very massive because it's really creating a big indentation, where the red one barely does anything at all because of its very small mass. And then if we kind of extend this idea of warping of space-time, we can think about some of the objects that we've looked at so far that have varying degrees of gravitational fields, like the sun, the white dwarf, the neutron star. See how strong, how big a deflection this causes. And essentially the black hole is almost like a hole within space and time at a certain location on that indentation, or that hole is where we find the event horizon. It's kind of crazy, but I kind of like this idea or this explanation of gravity because it makes a lot of sense if you think about it and can visualize it. And so basically the travel of light on this warped surface is why light would bend under the influence of a gravitational field. And so you might say, well, that's fine, you sound like a nut job, but can you prove it? Is there any sort of confirmation that this is actually happening? And the answer is yes. So in this picture from our book, we actually see that there's a star. If we could observe a star at different times, depending on whether or not that light from that star has to pass near the gravitational field of the sun, that we can actually see that in certain situations, like here's the star, but as the light's traveling towards Earth, it kind of gets bent a little and comes towards us. So then when we sort of trace that back, it makes it look like the star is over here, but it's actually here. So that light actually has bent. And we have been able to observe things like this, even with not just the sun, but also different objects warping or changing the direction of light that comes to us. And some other examples maybe we'll see later with galaxies is called, we can actually sometimes see two images of a galaxy because of what we call the gravitational lensing. And so now we're just going to talk really quickly about detecting black holes. When we're talking about this, we are not actually going to talk about yet the supermassive black holes that seem to be at the center of our galaxies, but we're going to talk about sort of stellar remnant black holes that are relatively smaller in size. And so basically the case is astronomers have figured out the best place to look for these black holes is at binary star systems. I mentioned in class before that because stars form in clusters, it's actually pretty common for you to have two stars that are in a binary star system. And so a binary star system is two stars. You might have one big star and one little star. And I said that they orbit around a common center of mass. What do I mean by the center of mass? I always like to think of it as if these two stars were sitting on a seesaw, where would be the pivot point so that they would balance? And that would be the center of mass. If you've ever played on the seesaw with friends that aren't the same size as you, you might know that smaller people have to sit further away from the pivot point of the seesaw, and bigger kids have to sit closer so that they can balance. And so these two stars in this binary system would go orbit around this common point that actually nothing is there. So sometimes it could be possible that in a binary system, one of the stars has gone supernova and has collapsed into a black hole. So we might look for a binary star system where it seems like the one star that we can see is orbiting around some point, so we can see its motion detected through its spectra and other effects of its light. But then there's not another star visible to us. But maybe, and so then we'd have to kind of do some calculations and say, well, this star's moving, and it seems to be moving around a common center of mass. based on its orbit, what would be the mass of the other partner star. And if that inferred mass through our calculations is bigger than 3 times the mass of the sun, then it seems pretty likely that that other partner is actually a black hole. And sometimes we will see signs of this because the gases, if the partner star becomes goes into its giant phase and swells big enough, the gases from the outer part of this star could be actually sucked in by the gravitational field of the black hole. And as those gases accelerate towards the black hole, they will emit X-ray emissions. And so this is a way that we can confirm and identify and observe sort of basically probable black holes in our universe. So hopefully this is kind of interesting, kind of crazy, and that's black holes. We'll probably, like I said, revisit black holes when we go and study our galaxies, which is where we're going next. And those will be a little bit different, but the ideas will still be the same. All right, have a great break, and I will see you on the other side.